In this lecture, we begin our study of second order differential equations, which are genuinely second order in nature. And as always, right, so it's useful to start with the homogeneous version of the differential equation, right? So later on we will look at the inhomogeneous differential equation. So at the moment we are concentrating on second order linear equations with constant coefficients, right? So I will give you the explicit form in a moment. So but in this lecture we are going to discuss second order homogeneous linear equations with constant coefficients. We will lay down the the method for solving such differential equations. Okay, so the differential equation of interest is the following. So you have a2 times d squared y by dx squared plus a1 times dy by dx plus a naught y is equal to 0. So a2, a1 and a naught are all constants, and the right hand side is 0, which is what makes it a homogeneous differential equation. Later on we will see how we can use the solutions from the homogeneous differential equation to work out the general solution of the inhomogeneous differential equation, right? So we have seen already with first order differential equations how even when you are given an inhomogeneous differential equation, when that is of interest, it's useful to find the solution of the homogeneous counterpart of the same equation and then use the solution from there to find the general solution, right? So we will see explicitly later on how this works out, but for this lecture we will concentrate on this homogeneous differential equation second order with constant coefficients. So let's look at a specific example. Suppose you have d squared y by dx squared plus 5 dy by dx plus 4y equal to 0. Now it is convenient to think of this as in this operator language. So you think of this as d squared plus 5d plus 4 acting on y equal to 0, right? So you have some operator which is acting on y and it gives you 0. And what is this operator? It's the differential operator, right? So it's a linear operator. So it acts on y and it gives you dy by dx. And if you act with another d, that's going to give you the next derivative. So that is written as d squared, right? So we will see the usefulness of this as we continue this discussion. So the idea is that you can actually treat this operator expression as like an algebraic expression, and in fact you can go ahead and factorize this, right? So and there are two convenient ways of factorizing this. So I mean, if you thought of this quadratic form d squared plus 5d plus 4 as just you can equate that itself to 0 and think of this as a quadratic equation. You will get two roots, and so that can be used. So in this case the roots are 1, -1 and -4, right? So therefore you can factorize, right? So this quadratic form can be written as d plus 4 times d plus 1 if they were usual variables, and it turns out that this operator equation itself can be written in this form d plus 4 times d plus 1, right? And so the corresponding quadratic equation is called the auxiliary equation, and the roots of the auxiliary equation are of great importance in finding the solution of this, which we will discuss ahead. But before we do that, let's quickly familiarize ourselves with this the algebra of these kinds of operators. Let's write down a few properties and see how they work out, right? So we are familiar with linear operators from linear algebra. So this d is also a linear operator, right? So all these properties corresponding to linear operators will follow through. Let's check a few properties which are useful for us. So one is like what we just already said, d plus 4 times d plus 1, it doesn't matter how you factorize it, d plus 1 times d plus 4 and d plus 4 times d plus 1 really are the same, right? So two operators are said to be equal if what they do is the same, right? So if two operators acting on the operators act upon a vector, right? So here in this case y, if d acts on y and it gives you what is the outcome of this operation if it's the same, right? If you are given two different operators and whenever it acts on any y, the result must be the same. When that happens, they're equal. So the statement here is that this property that we can show is d minus a times d minus b is the same as d minus b times d minus a is the same as d squared minus a plus b times d plus ab for constants a and b. Right, so another way of saying this is this, these two commute, this operator d minus a and d minus b, right? So that's another way of saying the same thing. So let's look at how this comes about. The way to see this is to operate with this d minus a times d minus b on y. So that's the same as d by dx minus a times d by dx minus b acting on y. So this part must be made to act on y first. So then you get d by dx minus a times dy by dx minus dy. So it's a linear operator. So there's this property of distributivity, and then again once again you use the property of distributivity. So you get, you operate with d by dx, so you get d squared by y by dx squared minus a dy by dx minus b dy by dx plus ab y. You can convince yourself, right? So each of the terms on the left hand side will act on each of the terms on the stuff that is being acted upon. So you get all these 4 terms, and then you can collect these terms. The second and the third term are really, just they can be summed. So you get a plus b times dy by dx with the overall minus sign. So you can collect all this and write it in this compact form as d squared minus a plus b the whole times d plus ab, the whole of this acting on y, right? So you can quickly see that it didn't matter if you had done d minus a times d minus b or d minus b times d minus a, you would get the same, and both of them would be equal to this d squared minus a plus b times d plus ab, right? So that's what this property is. And so the key point which I should emphasize once again is that this works out because both a and b are constants. If they had been operators, then this may not, such a simple commutation may not hold, right, like we will see. So therefore we have managed to show that this property holds. Let's look at another property which can be, one can write a more generalized version of this, but let's say dq plus 1. So instead of dq plus 1, one could have also thought of this as dq plus aq, and you are free to work that out, that more general version. So let's look at how dq plus 1 is equal to d plus 1 into d squared minus d plus 1. Once again, the technique is very similar to the previous property. D plus 1 acting on d squared minus d plus 1y is equal to d by dx plus 1 times this whole thing. Then you expand, then you get all these cancellations, the second, third, fourth and fifth terms will cancel, and then you'll be left with just d cube y by dx squared, d cube y by dx cube. So this should be x cube. So you get d cube y by dx cube, and right here d cube y by dx cube is equal, so this is the whole thing is d cube plus 1 acting on y. Therefore it follows that since it's true for any y, d plus 1, the operators themselves are equal, right? So d plus 1 times d squared minus d plus 1 is equal to d cube plus 1. So another interesting and useful property is this dx. So when the operator d acts on x, if you change the order of this, x itself you can think of as an operator, right? So it's just multiplication x d, then they're different, they're x d and dx are different. So in fact you can show that dx is equal to x d plus 1. So let's see how this works out. So let's operate with dx minus xd on y. So dx minus xd on y, you bring in y, so d must act on x times y. So that's what is meant by dx. And so you must first multiply by x, and then d will act on the result of this multiplication. So d will act on x times y minus x times dy. So but the derivative of x times y is the same as x times dy by dx plus y minus x times dy by dx. Overall outcome is just y. So we see that dx minus xd is actually just identity, it's just 1, right? So thus what we have seen is that these operators d and x do not commute, and this is not the first time you're seeing something like this. In fact, you have worked with the same kind of operators. You must have seen in quantum mechanics that the operator corresponding to position and the operator corresponding to momentum, they do not commute. But what is the operator commuting to position? It's x, and the operator corresponding to momentum is like the derivative, which is what we have. There is a constant I times h cross minus I times h cross, doesn't matter. But the key point is that there is this non-commutativity between x and d. So which here in this case turns out to be dx minus xd is equal to 1, right? So there you get x comma p, the commutator is IH cross, right? So that comes because of the factors involved, right? So this is not unfamiliar at all. So let's use this to see one more commutator. You can work out more complicated commutators, and perhaps that will be part of homework, but just to get a hang of this, the algebra around this and how one should exercise care, let's look at one more example. D minus x times d plus x and d plus x minus d minus x, they don't commute, right? It's quite different from d minus a times d minus b, right? So I said d minus a and d minus b, they are the same, but if you take so in fact what I mean to say is, so let's look at this commutator d minus x and d plus x. So this commutator, so it is d minus x times d plus x minus d plus x times d minus x. So if I work this out, d minus x times d plus x is d squared plus dx minus xd minus x squared, but dx minus xd we have just shown is equal to 1. So I have d squared minus x squared plus 1. So I mean, if in regular algebra you would have thought that something like a minus x into a plus x is just a squared minus x squared, but here you see you get this extra 1, right, which makes all the difference. And on the other hand, you should convince yourself that if I do d plus x times d minus x, I get d squared plus xd minus dx. So there is a minus sign here, minus x squared remains as it is, so you get d squared minus x squared minus 1. So if I subtract these two quantities, so I will get a 2. So in fact, if I do this commutator d minus x comma d plus x, so I get equal to 2, right? So they don't commute, right? So that's the main message from this discussion. Okay, so after this slight detour on operators and how they act on, how some of these properties of this operator algebra is concerned, let's get back to our original discussion. So we were looking at the second order differential equation, d plus 4 times d plus 1 acting on y equal to 0. Now, so we have just argued that it doesn't matter whether I think of this as d plus 4 times d plus 1 acting on y equal to 0 or d plus 1 times d plus 4 acting on y equal to 0. So we see that the solution to each of these differential equations, if I somehow manage to solve just d plus 1 acting on y equal to 0, or if I solve d plus 4 acting on y equal to 0, right, each of these solutions is also a solution for the full differential equation, right? So that's because d plus 4 acting on 0 will be 0, and likewise d plus 1 acting on 0 will be equal to 0. So but each of these is just a first order differential equation, linear first order differential equation, homogeneous, and we know how to solve it. And so in fact we can go ahead and write down the answer, right? I will allow you to check this. There are these two solutions and they're linearly independent solutions, which you can check if you wish with the help of the Wronskian of these functions. But for sure these are two linearly independent solutions of your differential equation, and an arbitrarily linear combination of these two linearly independent solutions will be the full general solution of this problem, and that's it. So you see how we managed to, for this case, just solve the first order differential equation and then write down the solution of the full second order differential equation. So here it turns out to be c1 times e to the minus 4x plus c2 times e to the minus x, right? So all we have done is actually just to use the auxiliary equation, find its roots, and using that we are able to write down the solution of the full second order differential equation, right? So the auxiliary equation itself, there are a few cases one should consider, right? Suppose the auxiliary equation yields equal roots. Suppose you had a scenario where you have d minus a times y equal to 0. Then, I mean, it seems like we have only one solution, which is e to the ax, right? Only one linearly independent solution. So how do you write the general solution for a second order differential equation? So it turns out that x times e to the ax is also a solution for this, right? As you can check, right? So I'm giving you like a prescription here. You can check that this works out. So in fact, the general solution for this scenario is given by this expression ax plus b times e to the ax, right? So you have x times e to the ax is one solution, and just e to the ax is another linearly independent solution, right? The linear independence can also be checked with the help of Aron's skin, if you wish. So then there is a third scenario which also one should be aware of, right, which all appears frequently, and that is when the auxiliary equation yields complex conjugate root, right? If one of the roots is complex, the other also must be complex, right? We know this from quadratic equations, and indeed the two roots are complex conjugate roots. So you can have a scenario where the roots are alpha plus or minus I beta, and in this case the general solution will turn out to be e to the alpha x times a times e to the I beta x plus b times e to the minus I beta x, right? So once again you have these two free constants. So alpha and beta are already given to you. You have got this from the differential equation in question. So you start with the differential equation, find the auxiliary equation, find its roots, and those roots turn out to be alpha plus or minus I beta. So there are these two numbers alpha and beta which are known to you, and therefore you just simply write down the solution. Y is equal to e to the alpha x times 8, a times e to the I beta x plus b times e to the I minus beta x. So a and b being the free constants corresponding to the second order differential equation. Let's just quickly look at one example. So if I have this differential equation d squared y by dx squared minus 6 dy by dx plus 9 equal to 0, the roots of this auxiliary equation turn out to be just 3. They're repeated roots, so you get d minus 3 times d minus 3 times y equal to 0. So the general solution according to the above prescription is ax plus b times e to the 3x, as can be verified directly. You just take the final solution and plug it into your original differential equation, and you can check that indeed this is the correct solution. And given the fact that it has two free constants, that's as general a solution as you can get, because the second order differential equation will have precisely two free constants, considering that it's linear, right? Okay, so we have in this lecture managed to chalk out the prescription for solving a homogeneous second order differential equation with constant coefficients. That's all for this lecture. Thank you.